suddenly I know, oh, it's allergy. So I think information matters. Today, because my title, I mean, my work title is a professor of climate. And when everybody hears the word climate, they think about warming. But during the warming climate, can we turn off this light here? All right, great. During the warming climate scenarios, we actually can experience extremely cold winter times. And a lot of times those this kind of cold weather events will through people's belief or perspective of balance, thinking, hey, aren't we in a warming climate? Isn't it about global warming? Why would we have cold weather? And increasingly cold winters in some areas. And then also, how does this affect our natural resource and affect our economy? This is something I want to combine together. Like, oh, we all talk about disasters, and disasters means the government losing money. But I'm gonna share some story today that if you capture all this information, you could actually make money. So let's just do a very quick review for what happened last year. It was not long ago. It was actually last time I visited KAIST was in November last year. And then during the time I said yesterday, which means sometime in November last year, New York or Northeast US has been hampered with heavy snow. Now this year, the shift to Western US, where I come from, Utah. Utah is a ski town, the ski state. So they have record snowfall, record. That's really means it's it broke all the record for snow. And this is in other parts of the world. And also from Canada to Great Lakes regions, you get ice rains and your house will end up looking like this. You know, it just keep freezing and then build up. And it's very hazardous. And every year people die from all sorts of things associated with that. So to understand why in a warming climate, we will still get cold of increasingly cold weather, we have to understand jet stream. Jet stream is just high speed winds in the upper atmosphere, because the thermal imbalance of the entire Earth, it creates these boundaries. So this jet streams basically can separate colder air in the north, warmer air in the south. But because they also meander like this, that you will have cold, occasionally very cold temperature in some places versus very hot weather in different places, depending on the jet stream. So that's an important concept. So I want you to grasp this idea. Because of the jet stream, very cold air has been trapped in the polar regions. And no matter how much warming, in the future is going to happen, the Earth still will form this warmer air, cold air pocket in the polar region compared to the warmer, more southern regions. So there's also something called the polar vortex. This is a stratospheric, very high level phenomena that also means it traps the cold air. So if you look at the Earth from this angle, basically you see these rotating features, and that's how this jet stream trap cold air. So it's not just a very shallow layer of cold air. It's actually a three-dimensional pocket of cold air. So because the jet stream will change, and the way it changes is just like people have a mood. Your mood is different every day. The jet stream can also split and become very wavy. And if they reach far south and reach, say, New York or Michigan, then they will bring those very cold air down. So this is more like a basic state of the Earth's climate. And during winter time, you will always have this pocket of cold air. So this is the fundamental knowledge about why will we still get cold, because there will always be cold air. Just like your fridge, you still always have a freezing, the freezers for that. Okay, so then we can talk about waves. The jet stream is essentially high wind speed zone. And winds are what? Winds are moving air. So moving air and moving water, same thing, is a fluid. So if you apply the fluid dynamics and then you put some sort of like a terrain or other things, then you will create waves like this. Sometimes the wave will stay in one place, even though your wind keeps going. Your wave, the trough and ridge will stay in one places. They form something we call stationary waves. Means they are almost not moving. They move, but they over time stay in the same place. So if you look at the winter stationary wave or the winter basic climate of North America, then you're going to see something like this. Okay, so you can see this is like the high winds area, but then there's a small trough and there's a trough. This is the ridge. We call it a ridge, high pressure ridge. So if you take the mean, the average out of the whole globe, then you will reveal a high pressure area here and low pressure area here. This is long-term climatology. This is the mean state of what we call as a North American stationary wave features. So this is a higher level, upper level at about your commercial jets flying altitude. This is more towards the surface. In the mean state, you can see that the temperature, the surface temperature distribution has this east-west divide. Okay, so the Western US has a more of a warmer or higher temperature versus the eastern part is a lower temperature. So this is the basic state, right? We have to know that, every winter, if you average for 30 years, this is what you see. So the winter climate regions are actually divided across the whole continent. So this is just a recall of what these waves looks like here, right? And throughout the past 40 years, and with the U.S. government's tracking of records, they realized that what they call as $1 billion disaster events caused by weather or climate anomalies has undergone dramatic changes. During these 20 years, up to 2005, the number of drought-related or heat-related disasters are distributed something like this. The number of freezing or freeze disasters are here. Usually, when you have event like that, it's because of a very cold air that move across the U.S. and what's in Florida, sun-kissed oranges, right? And then they got frostbite and they got a lot of agricultural damage. But during and after 2005, during these 11 years, the number of drought-related disasters and the freeze-related disasters increased dramatically. So this is about 10 years, this is about 20 years, and yet during these 10 years, it has at least twice more of the events than the 20 years, which means it has increased 4 times, roughly. Okay, so you compare to this kind of divide, does that imply, doesn't that imply that this high pressure and low pressure separation has amplified, right? That's the only reason physically can cause this part to be warmer, this part to be colder, leading to this kind of disaster divide, right? And there's a way that we meteorologists can track their historical changes. We throw in this term called dipole. Dipole means you have 2 polarity of opposite phase, right? And we just borrow this term. So you can pick up this high pressure and then minus the pressure over this low pressure region, then you form a dipole index. Okay. And we also test the variance. The concept of variance is like this. You can see the variability, but you can also measure how much they change. So the indication would be simplified. So let's see what it looks like. Right. So if you do this high pressure minus low pressure at the upper level, you're going to form a time series that looks like that from 1950 to all the way to 2017. And you can see that there's a trend, right? So it means like this high pressure and low pressure system over time has amplified. That explains the $1 billion disaster statistics change. There's also something that is of interesting is their variability, their variance also changes. This blue line is what we call a rounding variance about 15 years. So you just do the variance of the previous 15 years and plot it on the last year. Then you can form something like this. So we can see that not only that this high pressure, low pressure wave structure has amplified over time. Their changes also amplifies too. So it's like a person grow up and getting angrier and happier, angrier, happier, more, really like a human. So how do we understand this kind of change, whether or not it is related to climate warming? You have to simulate that. And some of you are already climate modelers, but those of you who don't know, climate model is just a set of mathematical equations that you solve and integrate it over time. I was just demonstrating something is an app in my MacBook that you can run. Okay, then with those tools, then you can start to run a very diverse sets of equations or of scenarios. For example, you can change the beginning conditions and the result will really diverge, right? And that's normal. That's very normal. It's just like a traffic conditions. But over time, then you can average, make a good statistics of all these different conditions. Hopefully, the randomness will cancel out. And what's left is the signal. And that signal, depending on how you simulate the model, usually climate scientists were focusing on these three types of forcing, which means in this case, you increase the greenhouse gas as if we have observed in the past and also project in the future. You can also put aerosol. Aerosol, if you don't know what aerosol is, look outside the window, the haziness, those are aerosols. Okay, aerosol has a cooling effect because it blocks sunlight, as simple as that. So the surface temperature, the surface near surface atmosphere will be cooling. And then you got natural forcing. Natural means volcano. When you have a volcano eruption, what it erupted also blocks sunlight. And then you also have the sunspot cycle. So you put those together, then it becomes all forcing, and supposedly all these all forcing experiments, simulations should track what we observe in the future, in the past. So you can see these four different lines, right? The historical simulation is the black one, right? And on top of that is the greenhouse gas simulations. And you can see the reason is on top of that because, it could get, our temperature could actually get higher if it wasn't for aerosol, which is this line here, the cooling effect. Now, I often get into this debate like, oh, it looks like aerosol is a good thing to combat climate warming. And a lot of geoengineers have proposed this idea. You can block sunlight so that you can curve the warming rate down to this rate, or hopefully to be flat. But then, well, it depends how you want to die. You want to die from heat stroke or you want to die from air pollution. And you have to make a balance. So back to this dipole things is that you can simulate the Earth system using all sorts of all those scenarios and do a diagnostic study, right? And then this line here, this is one of the simulations. So again, this blue line is observation. Remember, this is the variance. So it's how they fluctuate. So the increase here you're seeing indicates how volatile, how big of a change it will become. And all those bars, the orange bars, are simulations. You're only seeing one number because I use an ensemble, an average, but it came from about 40 different scenarios produced by a climate model. And then you can also see what the future looks like. And we project the future warming to continue. Therefore, the future climate will be warmer than the past climate. So you are seeing this projection that indicates at least over North America, the high pressure and low pressure system, how they see so will amplify, okay? So it means that the extreme events will happen more and more often. So in California, which is here, which is right underneath this high pressure, that when the dipole index becomes really high, what it means is you got a very much amplified high pressure here, combined by low pressure in the eastern US. And the high pressure means what? Fair weather, more sunlight, trapping more heat, it means drought. So 2014, 2015, you know, and then 2019, or the past actually 3 years, we have seen that the water resource in California have depleted severely. But in between, there was also very serious flooding events caused by excessive rainfall. And that's when you flick back. So the index here suggests that you not only will see high pressure and low pressure amplify, you're going to see the reverse. So when the high pressure becomes much dampened, then what it means is that you got more of the frontal systems bringing more of a moisture, and then you can see that this is the same reservoir, you know, from almost dry to overflow and destroying the spillway. So the following analysis might get a little bit tricky and then tedious and boring. I want you to not try to understand what this means, what they are showing, but just to listen to my interpretation of this. We have to be very sure that there is a signal, and this signal is just not some sort of a random noises or coincidence. So we have to do a lot of different testing. One of the testing we can do is to use all the different historical data that was compiled by different ways, right? Hopefully you can, just like all the people here, if we want to decide something, we have to find consensus, common interest. That is what it's trying to do. And then we can compare that with the model projections here. So we basically, you're seeing, despite the up and downs, you're seeing a gradual increasing trend as the climate warms, right? And it goes back to 1850. So we are talking about 160 years of record, rather than just the future 100 years. And we can also use tools, climate models, to simulate the ancient past, the ancient time of the Earth, right? It's called paleoclimate modeling. And you can prescribe different conditions and appropriate at the time, and then to simulate the climate. So by doing so, you can extend the time series back to almost, I would say, 20,000 years ago. You can really run that. It's quite fun if you have the tool. You can run from the Jurassic era, you know, in the dinosaur era, and all the way to compare that. Now, the reason we do that is because the Earth has gone through these glacial cycles. The interglacial phase, then the interglacial phase, glacial phase. Actually, I should do the opposite things just to indicate the temperature. And so for the past 20,000 years, the Earth has gone through a warming phase. It came out of the glacial phase. This was the previous glacial phase. We are actually in the interglacial phase. Okay, so we're supposed to fall back into the glacial phase again, but very slowly. So you can see that during this time, the temperature has increased. It's indicated by the green line and the orange line, assessed from and inferred from different sources. The dipole variance index follows the temperature, and then all the way to here. Now, why is it coming down? Because remember, if we don't add greenhouse gas forcing or anything man-made, the Earth will be entering a glacial period again. But it did not, right? Because of the anthropogenic warming. Now, this is how the future global warming under the business as usual scenario will look like for the future. For the future, so you can see that the temperature will increase to 4 degrees Celsius more in the next 60 to 80 years. And you can see how would that compare to the dipole variance change, right? And during the same period of warming. So if we compare that, and then you can put them together into this. So it's supposed to transition, but it didn't do it. It's okay. What I was trying to show you is by this pure gas, I should say educated gas, you can already see that if the Earth increased for 4 degrees more, the dipole variance will increase basically from here to here. That's almost like a level higher. So it means that the winter climate variability will amplify. Okay, it means a lot of things. It just means that some years you will be severe drought, very bad drought. But then in between, you're gonna get flooding events, right? Like this here, basically. And we can also use different tools to track backward. So Professor Kim mentioned about applying climate science with different disciplines. This is one of the example. Well, we don't have so many stations, modern stations in the past. How do we know climate for the past, say, 500 years or 400 years? You can use trees. So because in the middle latitudes, a tree growth reflect climate conditions. They form tree rings, right? So the ring width reflects how favorable or unfavorable the climate condition was to that tree. So you can measure that and then infer and reconstruct the climate conditions. You can also do an isotope analysis to decide how much weight the different form of isotope is to infer the moisture conditions, and to reconstruct precipitation at the site of the tree. Okay, and by doing that, this is my colleague Steve Volker. We are in the process of completing a project in which he collects the trees, life and death, from Great Lakes region and try to do an isotope analysis and also tree ring analysis to reconstruct winter conditions. And then another collaborator and also other scientists who contribute data openly will provide some sort of a lot of tree ring data in California. So we can use these two to reconstruct this dipole index, right, with more of an accuracy compared to purely simulate or educated guess results. And that's something we're doing. It's very different. So we have gotten some preliminary result that shows that the predicted, I should say, tree ring isotope reconstructed dipole index, which is this bluish color, and the actual dipole index have a very good correlation. So you can see that by completely using a biological, ecological response, you can reconstruct the climate response with such a good accuracy. So that's part of the reason, I feel so excited collaborating with different fields of scientists, because we actually end up seeing the same thing. Their job is much harder. They have to go to the field, really call those data out. Now, like me, I'm just sitting in front of computers in the air conditioned rooms. They invite me over. I say, no, I don't like to hike. I'm a city boy. You go collect your data, I'll analyze it. So that's how we collaborate. All right, phase 2. I'm showing you this newspaper in Chinese because this is back in 2017 in December. I was visiting my hometown in Taiwan. I was born and raised in Taiwan. And I read this piece of newspaper. It's an actual newspaper, not the online ones. And I was reading the finance section, not climate or science, finance section. And what it says is Arctic cold air led to the coldest new year in 50 years, right? And what happened? The US natural gas price shooting up. And I start, that's the very beginning. I mean, this the exposure of my interest into what's known as the natural gas market. Fast forward, and I start to check. That was the time when I start to realize that making money is still very important in our life. Do not forget that. Continue to work hard, study hard, chase knowledge, but save money and make money. You won't regret it. So I look at this. Just pick one of the energy stock index. And, it's true. From here to here, there has been a 20% gain in prices. It continued to go up. And then this was when the New Year cold spell actually happened. So somehow, all those people, these people trading stocks, has a magic of knowing that this New Year cold spell will happen like 2 weeks before. How did they do it? Well, with a forecast model. You just look at the forecast. So I realized a lot of people trading natural gas, they are actively looking at the model prediction, weather prediction, for as far as possible. And now the common, the publicly accepted accuracy of a weather forecast is 10 days. Some people will tell you 2 weeks. 2 weeks is a little bit stretch. 10 days is pretty much the confidence start to fade. So it's about 10 days and they start to trade. So the gas price start to increase. Then after I returned to the US, I read this news. It said a small team of traders at Goldman Sachs, is a big financial company, they made $100 million by trading natural gas. Now, $100 million is something very attractive. If I have the means, I want to try that too. But how do they do it, right? Those are not meteorologists. Those are not atmospheric scientists. How can they see something that I didn't see that triggers my interest? So what happened in 2018 was this kind of climate patterns. Now you're seeing by the color of it, you know this is a warm anomaly. I mean, this is warmer than usual climate, combined with colder than usual, very cold, eastern US. And this pattern, I have seen it many, many times. In the beginning, I introduced you this divide, right? And in 2015, same thing. And 2015 also triggered a natural gas shortage, which has led to some energy crisis, some newspaper calling. And the year before, they call this polar vortex because all this cold air trapped there. You know, states like Minnesota, whose residents are used to cold, they still cancel schools because it's just way too cold, right? So collaborating with Professor Yun at the time, we published a few papers that got immediate attention, you know, how we link these changes to warming climate. At the time, no one was really looking at it. So we were kind of the first to identify this linkage. And later on, I was lucky to obtain a Department of Energy funding into looking at the climate variability and change, how it related to cold winters and how it related to energy. And this is a analysis that I'm gonna introduce you first, because then I will show you the results. In terms of climate diagnostic, climate data analysis, you have a certain tools. Those tools, just like the medical doctors, send you to take some X-ray, blood test. We have some tools too. One of the tools is called correlation map. This is a very good tool that you can use something as simple as a correlation coefficient to apply on a spatial pattern and to find, you know, consistent changes or not. For example, if you pick somewhere from Western US, you're going to see an index that looks like this, right? If you pick another one, if it's close by, they will have some sort of they will be very similar to each other. So they will have a positive correlation. But if you move away, you might have something that appears to be negatively correlated, right? Or you have somewhere that has no correlation at all. And if you put all this together and give it color codes, then eventually you can form something like that, right? And when you form something like that, you start to see pattern. For example, I can say that this is where my university is. I can say that my university's drought pattern, I was using drought index, has this dipole or this seesaw patterns. When we are in drought phase, you know, New Mexico here will be in a wet phase or vice versa. We can say that. So this is a good tool that we use, and I'm gonna show you later. Then you can start to do different time period, and you can start to find different patterns as well. So these patterns will change according to the atmospheric conditions, right? So I wish you can understand that. Now, back to the natural gas market. The US operates the natural gas in a very different form compared to the rest of the globe. And I won't read it. I'll let you just read it. There are two major differences. In terms of the pricing, it's completely decided by free market. There's almost no national influence. I believe in Korea, natural gas prices is heavily regulated by the government. So you will not see these fluctuations. Now, the next thing is that the natural gas also in the US is an exporter. It has excessive natural gas. So it exports to outside world. So it controls, you know, the fluctuation actually has the lingering rippling effect to the entire global natural gas market as well. And also, and some physical differences that the natural gas in the US are mostly stored as a gas form underground. Why is that important? because the US is so big, they have so much depleted aquifers, natural gas mines, that they can pump natural gas into it and just put it there as a gas, as opposed to if you drive around some industrial park, you will see those big metal balls. Usually they put liquefied natural gas inside. That's how most of Asian countries store natural gas, liquefied form. Right. So, but the liquefied form, you can put it there year round. This, however, goes through a cycle, because when the demand is high, when it's a winter season, you have to pump it out, extract it, right? But you cannot always pump it out. You have to inject it. When do they inject? When the weather becomes warmer, so no one is using that for heating or energy, then you pump it in. So they form an annual cycle that looks like that. From January to December, you are seeing this average line here as a gray line. So this is when people are using natural gas, when they pump it out and supply it to all 50 states. And then around April or May, and people no longer need to heat up their home, they stop extraction and then start to put the natural gas back into those reserve. So they went through this 6 months pumping, 6 months injection type of cycle. So when it's time around fall, that you start to approach the next extraction phase, this is when people start to guess or trade natural gas. They will start to think how much of a demand this year will be. Could this be a very cold winter? Could this be a shortage of supply? If so, they increase the price, right? They're gonna collect more. If they want to store more and collect more, the price will go up. And if not, then the price will come down. So this is where the active trading starts. Now you can look back to all the different years. This is the past 6 years. And there's one extreme cases was in 2014. 2014 saw the energy crisis. At the time, the natural gas reserve went below 1,000, I forget what the unit is cubic feet or something, billion cubic feet. So 1,000 is actually the margin. That's when governments say, okay, no more extraction. We need to reserve natural gas for emergency. And the price will go crazy because people are like, oh, wow, we're gonna run out of natural gas. I'm going to buy more. Then the price goes up like crazy. So those traders at Goldman Sachs, they saw this. They start to put money into the low prices period, which is warm period. And then they just wait. They wait. 3 years later, 2018, the same thing happened. The price went up, and that's how they made their $100 million US. Got it? I can make $100 US. Now have to be million. I'll still be very happy. So now it's the data analysis phase. You can actually see all the 40 years of natural gas storage levels, and you can track that, and you can compare that with their variability. So, I personally like to simplify things. If we're in a time series like that, well, it's nice to see the seasonal cycles, but you don't really need all 12 months to do an analysis like that. You can just pick up the minimal level. Sometimes it's in March, sometimes it's in April, doesn't matter. You pick up the minimal levels, and then you compare with the natural gas spot price. If you don't know what spot price is liquidated, it floats. It means like before the end of trading day, this price is negotiable. It's like a bidding, like, how much do we want this? 50, 50, 55, 55, 60, like that. So it goes up and down. That's called spot price. So you can see that even though the natural gas price overall has these slow up and downs that kind of like fit into this interannual year-to-year variability, there was always these sharp increases like that. These sharp increases, which indicates something unstable, is how you can make money from. Now, I keep saying making money, but I really want you to focus on the variability, okay? And so, but I still give you some example. Within 1 month, the natural gas price increased this much. And actually within 1 week, it increased about 24%. Okay, so if you really see that, if you put $10,000 in there, you're going to get, you know, $2,500 more. Well, that's not bad, right? Very good return. But then they don't stay long. They quickly collapse, right? So the first time I did it, I'll just admit I have done it, and I was overconfident as a scientist and not confident enough as a trader, so end up buying high and selling low, losing money. It's a greed, and anyway, so we come back to see this time series. I've been updating that. This was the 2018 case. You can see the sharp increase here. It's from here to here, it's roughly, I would say, almost 100% increase of the price. So you can, if you put the money in, you can actually get 200% back on that. And you can keep updating that, right? 2021, the price went super, super high. Of course, that's not only associated with yet another very cold winter events, but also Russian war on Ukraine. So this time is not so purely climate. However, the timing still tells you, it's what we call a compound effect. There's a war, we know it will be natural gas shortage. And then there's also the cold winter. So when the two combine, you can see the price went from here to here. That is amazing because it actually, the range, the last time you see such a change was in early 2000s. But you can see that this kind of peaks. This is how a lot of traders, they wanted to bet on energy, especially natural gas. Because if you can wait, if you have the money and if you have the time, all you need to do is to find a low spot and then just wait. But the art and the knowledge comes in, and how much do you want to sell? Do you want 20% and sell it? Do you want 50% and sell it? Because if you don't sell it, guess what? Collapse. Okay, you're gonna lose money. So we are scientists. We don't focus on money. That's just a lie. But we also want to focus on the science. Now, remember, I just introduced you this correlation map analysis, which means that you can use this minimum storage. I detrend it to get rid of the, just the man-made conditions in the natural gas extraction, and then correlate with what we call the upper level. It's a mouthful. I just treat it as upper level pressure. And if you do this kind of correlation, you form patterns that looks like that. You got a positive area here, negative area here. Okay, this is inverse. So you can compare to the 2014 California drought. This is the actual climate anomaly patterns. You have a high pressure here, low pressure here. That looks very similar to this pattern. Very similar to this pattern, which means the dipole things, stationary wave things that I introduced before, has direct consequence or impact on natural gas storage, right? So let me just remind you, this is what it was like. Not only in California, you have a depleted reservoir due to, there's the most severe drought ever recorded at the time. You also have what they, excuse me, what the media call the polar vortex in the eastern US. The entire Lake Michigan froze. And so again, the dipole index I have showed you before. And if you correlate the dipole index with the natural gas storage, you have a very high negative correlation. It's negative because the positive phase will induce a negative reaction of the negative reaction, negative storage. The less of a storage, the higher the price. Now, if you focus on the past 30 years, they have an almost perfect correlation here. Now that's becoming interesting because you see, I pick up March or April minimum of natural gas storage, right? And this is what? This is November, December, January index of circulation pattern. So if you know something this early on in November, December, and looking at the climate pattern, you can theoretically predict what the March minimum of natural gas storage is. So that forms is like an empirical prediction, but it's a time lag in between. And you can flip it, you can also see the trend. So anyway, skipping that, my student Jacob and I on the invitation by Professor Hyungjun. At the time, we did a small study on capitalizing this relationship between the dipole and the natural gas consumption variance, and then produce this consumption variance. This is a purely statistical, and then you can project those kind of consumption variance and storage variance based upon climate conditions. You know, the very high, very significant correlation coefficients between the storage and the circulation pattern, reconstruct this and predict this consumption variance and the storage variance. So what you see is from in the future 80 years, 60 years, you can see the variance will increase, either in the storage or in the consumption, which reflects the market price. But the market price and the spot price is very highly nonlinear, so we didn't really attempt to do the price forecast on that. But this can tell you at least one thing, that the kind of variability you're seeing is projected to increase as the climate warms. So the warming climate projection not only just increase global mean temperature, it increase the possibility and severity of cold winter as well. So if you look at this, we go back to look at this price again. What this consumption and storage projection implies is that this kind of fluctuation will increase too, which means if you pay attention and then have capital, you can get a very good investment decisions out there. Okay, just as long as you don't come back to me blaming if you lose money, and I will support you to do that. Encourage you to do that. So that's how I prepare what I prepared for today. Again, my focus is on the variability and how an amplified variance can affect our economy. There's a lot of bad things associated with energy shortage and that's because of this floating prices differences. Even though it gives some people some aspect to make huge money, most of the time it actually hurts people because your monthly gas bill will change. Let's just say I live in a small house. I do everything I can to insulate the house. This month, I get a gas bill of $20. Next month, even though it was colder, even though nothing really changes, because the price changes next month, I can get twice as much of the bill. And it really hurts people with low income and marginalized community there. So that's my concluding remarks. That will end my presentation today. Thank you for your attention. Mm-hmm. 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 Yeah. Yeah. Yes. I'm very impressed by your question. So let me go repeat. Oh, okay. So you're asking that when the tree goes dormant in winter, and then but we sometimes like isotope, we want to extract the time when they are functioning. Therefore, you can measure the difference in isotope in summer or whole year round. How do we deal with that, right? It's a very scientifically insightful question. So let me see if I can go back to my slide here. I want to go back here. Steve, my colleague, had a very brilliant idea. Let's see the picture. So I skipped this slide and you caught it. And thank you. what he did is to take the springtime timing of the tree's isotope. They can track that, the timing of which, and then infer the winter time temperature. How did they do that? Because he only called trees that live alongside the lake, near not like an inner, but alongside the lake. The question is that, I mean, the catch is that the lake, if it froze during winter, and if it freeze hard during a very cold winter, then it's going to thaw, it's going to melt very slowly into summer or spring. That giving this time differences to infer back to how cold the winter is, even though the trees are dormant. I hope that, I mean, I'm very excited that you asked this question, because by the time I went through this slide, I'm a little bit tired. It's like, okay, I want to move on, and you called it. Thank you. Does it answer your question? Right. Yeah. So this, we are not directly inferring or reconstructing temperature. We are actually reconstructing the timing of the trees refunctioning, waking up, and use that to, and that's controlled completely by how cold or how much ice the Lake Superior was.
Hello. Can I ask a question? Hello, can you hear me?
Yes, please go ahead.
Okay, yes. I was quite impressed your nice talk, and I am not an expert in earning money, but my expertise in electronics, and I am quite interested that you mentioned, what is it, vortex or dipole, and you have shown one picture of the, well, what is called winter dipole or pole dipole in the North America. How about in the other continent or in the other hemisphere? Have you ever tried also? That is my comment. Okay.
Okay. Professor Song, yes. Thank you for your comment. Yes, we have tried other places, but there's two reasons why we focus on North America. The first reason is because I live there, and then it's where funding agencies are targeting. But there's a climatic reason as well. So the second reason is that it's a very unique place and combination of the jet stream and also the terrain. And the terrain is not only for Rocky Mountains. The terrain, I didn't show the slides, but the terrain impact of the jet stream, you can trace it back to Tibetan Plateau. So Tibetan Plateau disrupt the jet stream, making it to be wavy. And there is a phase of this high and low dipole pattern just happen to have to reside on North America. And then the Rocky Mountain reinforce that. So which means that the dipole with the size and stability, they, in the climate records only existed in North America, which making it a unique case. I hope that answers your question. Mm-hmm. Mm. Mm-hmm. Yeah. Okay. Yes. Okay. First of all, I'm not an economics expert, but I do know that the reason that U.S. natural gas market is so unique, and of course, we have foreign investment in going in and invest in the domestic natural gas price. It's not international. So I think that answers your first question. The second, the next aspect is you can see information here, but the next aspect is the U.S. is the net exporter of natural gas. So it make it way more insulated from international events. For example, I was really amazed by how little of the influence that the Ukrainian war has had on the wintertime natural gas pricing. It affects that outside the wintertime a lot, but then during the wintertime, when it happens, the variability, the supply and demand, and the cold weather outweigh that, right? But if you put it in a global, international natural gas price, it is not there. It is more geopolitical changes that influence that. So that's my observation. Mm-hmm. Okay, sure. Yeah, I'll try to summarize it here. I think I can use this image here. Now, from time to time, just like in Korea, some winters are very cold, some winters not so cold. Sometimes you have a 4 months average temperature that is actually not so cold, but you have 2 weeks or 1 week that is really cold, right? So those form a climate anomaly, as you see there. Now, this is the temperature differences. The blue color means is how cold below the average, and here the warm color means how warm above the average. So this kind of a change, usually people think it's random. Like here, you can ask the 2 professors here to predict Korean's winter 2 months ahead. It's impossible, basically impossible. We tell KMA it's possible, so they can support us, but it's very hard, very hard. But miraculously, or I should say coincidentally, in the continent of North America, because of its unique terrain, just like Professor Song online was asking, why here? That's because all the things I tried to explain in the beginning, how come we have the jet stream, and then how come we have the stationary wave, and how the US, is just uniquely situated. I mean, how the waves in the atmosphere uniquely situate over North America, making them to have this kind of a climatology. When I say climatology, it means basic state. Now, if you have a mean state that's looking like that, it means no matter how you change, you're going to follow this. It's a bit like our race. I'm born Asian. I can be sent to US from age 2 and become an American, but because of my parents, are still Asians, I will still be influenced as an Asian. And this is how it changes like that. And because the terrain, I skip a lot of the fluid dynamics part because I thought that, we really need more time on that. But I can assure you that this pattern, this high-low pattern, it doesn't change. Over the long time, it stays there, but it fluctuates. So it forms an interesting thing that, yes, it might be difficult to predict, but the deviation won't be too much. So I will conclude by saying human, like we all have personalities, but we all have mood changes depending on what happened last night, what happened this morning, and it's unpredictable, right? But because if you know my personality, you won't predict something that I will do something very crazy or very out of this boundary. I will do something very crazy, but within your expectation. So that's a bit like that. This is your personality. Fluctuation is your mode. So you have certain predictability. And when it comes to trading to something like this, all you need, you can never make perfect prediction, but if it doesn't go wrong, you may not get 100% of the increased profit, but how about 30%? It's still money. So I hope that summary helps answer your question. Thank you. Oh, in chat? Okay. Let's see. Oh, did I? Oh, okay. Did I? Oh. Yes. Yeah, right. Okay, so let's see. Okay, question. Due to strong dependence of data, one may think that it might be possible to use AI-based algorithm. I really hope so. The best spots. That's exactly make money. If the objective is to make money, yes, of course that's the objective. You know, but if we can save the world while doing it, it's better. It's even better. So, do you think this algorithm output might be a good hint? The AI technique, I see AI as a very advanced statistics. So what it would do is to capitalize on data that we could have missed, human eye have missed. And through simple statistic, just to reiterate how simple it was, like these two time series here, right? This is very simple statistic. You simply need to do a linear regression. You can already predict the minimum natural storage in March. Of course, it does not tell you how the price increase will be during October or November, but you have a pretty good idea that could be. And AI could certainly help extract a lot of the data that is buried in this kind of fluctuation. Now you see, these are, sorry, when you see time series like that, you have to wonder, what are signals? What are noises? This is this signal of noises. Is this signal of noises? Is this huge noises? Yes. I think that the answer is both. But how much of a component is that? You know, I can have my human perspective, but if using AI, I believe it will be more objectively to gather data like how the trading volume, the source of the volume, the you know, and also other things, financial that I don't even know what to say. But you can see these are signals. These slow up and downs. These are climate signals. From here to here, 2 years. It's a very long time. Why do they do this? Well, it's a signal coming from not only climate but also consumption and supply and demand, geopolitical changes can all make this signal. But these are supposedly noise. They don't really follow the pattern, but actually they do because the seasonality and because how people look at weather forecast and then put on bet. So I believe so. Yes, if there's an AI algorithm that can be trained to deal with data like that, I think at least it can help us more objectively predict how high this will be. Because you don't want to put like, okay, I purchased some shares here. I believe because historical record, it will be here. So I set my sell point here, but it didn't reach it and it crashed. Now we have to wait another 5 years. If you have a little child, 5 years from here to here, that's a very long time. You might need the money, and you might sell your share at loss. Or if you did it right, like this year, you could say, okay, I'm very conservative. I fear losing data. I only want 15% margin. So I set it here. Can you imagine the regret? Like, whoop, start to increase. I sell everything, but hey, it went up. It feels worse. So I think AI can help us produce something more of the range. The timing we know, but the range is something it's half science and half art. Thank you. Yes. Mm-hmm. Hurricane, yes, but hurricane is much more noisy. And of a lot of things in natural and financial worlds, most of everything are very noisy, including hurricanes. People start to make predictions about, for example, next year, how many will fall in Western Pacific. And they now have a certain accuracy, the number of hurricanes, because it's a huge ocean. we see the ocean temperature conditions, and you can build, okay, if ocean is this warm, if our high pressure move like this, we might have 10 rather than 5 hurricanes. But how many would that hit Korea? Nobody knows. Yeah, again, we like to tell our National Weather Service, yeah, we can know if you give us $2 million research funding, but it's very difficult. So yes, in answering your question, that also comes to the perspective of time. So if you want 2 months ahead information 2 months ahead, very difficult. 2 weeks, yes. 1 week ahead, almost certain. 3 days ahead, you better mobilize National Guards to send them to certain areas for disaster. So it's a rotating process, moving process. So if you combine that with, say, social scientists or government policymakers and form SOPs, and you move by this timetable, then things can be mitigated very well. Thanks. Yes. Mm-hmm. Yes. Okay. Yeah. Yeah. Mm-hmm. Health impact. Yes. Yeah. Mm-hmm. Mm-hmm. Okay. Yeah. Yes. Okay. You're asking how this kind of algorithm or application can apply to less developed countries, especially on natural gas and also on health, public health issues because of cold weather. It's a very broad question. I try to not say too much, not speak too long. I think the first question is we have to clarify where are those less developed countries are. Most of the middle latitude countries are developed. And those are the countries that will be affected by cold weather. If you go to Russia, Russians don't care about cold weather. They live in cold weather, in a way. It's the transition zone where you usually have a temperate climate, but it suddenly get very cold weather. That's when the society was not prepared for the situation that they didn't prepare for. Kind of like if here got 10 inches of snow accumulate on the road, you're gonna shut down the city. So if the countries are in the tropical areas, then well, A, they are further away from the cold weather impact, and B, how they use natural gas would be the first question you need to answer in order to frame your objective. Like, do they use natural gas? How much do they depend on natural gas? And are the natural gas supplied through pipelines or through gas tanks, propane? If it's propane, well, you can mitigate it by just put more, buy more when it's cheap. But if it's pipeline, then if it's shut off, it's shut off. If it doesn't shut off, the price increases. Then there's the next question: how does the government regulate those things? So it's convoluted, but I think it's very important to get to know this question before we move on to see the actual impact on less developed countries. So I didn't really answer your question. But this is how I would approach if we are to work on this together, right? And we need to set this clarification first. But yes, it can apply once we know more. Mhm.
with the companies, both manufacturing devices, home appliances.
Mhm.
Which state will be the quickest response? The prediction of the
Mm. It's always Wall Street people. But then you see this EIA, this thing. EIA is the government. It's called the U.S. Energy Information Administration. The EIA of the many government agencies that provides their statistics online, the EIA is one of the best ones. Their information are very thorough and easy to access. So a lot of people, they look into this and then they collect the data they need or simply throw into the data bank and run machine learning to get information out. Those could range from natural gas buyers, that energy companies for sure, the suppliers too, the one that runs those wells. And consumers, unfortunately, without the knowledge of this, consumers are almost always the last to respond or cannot respond at all.
related question.
Mhm.
Increase of the information sharing based on, for example, ChatGPT.
Mhm. Yes.
And do you expect that that will affect sort of information dissemination between the stock market people and consumers and the companies?
I believe it will. But that kind of information, I think that comes to the next question, the speed of information. We all know that Wall Street in the 80s and 90s, they absorbed a lot of nuclear physicists who had no job, found no job, and become engineers for Wall Street trading. So the machine trading has been there for 30 years. And they are doing those I forget what, this is a terminology for that. It's quick fractional trading, but very quickly, rapid trading to do that. And for some time, I believe there are existing algorithms to run this particular market as well. I just don't have access to it. So if somehow you can have improved AI algorithms and you combine with those rapid access for the trading, then yes, it could be. But I give you an example of my understanding of how tedious those traders are doing. They would actually go out to the information source of like a cables. Then they will buy property there. Then you tap into the cable to access the information before it sends to the New York stock market exchange. So how much time would it get? It's less than milliseconds. But that kind of information can make a difference during those rapid trading algorithms on everything else. Natural gas, I don't think we need that kind of frequency. High frequency trading is the word, high frequency trading. We don't need that kind of high frequency. So how do we make a balance between these? It's an open question. I do believe that it can be done. Scientists might, yes. Yeah, I never hide the fact that we always have a motivation to make more money. We make it applicable, right? And it will be beneficial for everyone. It's a free market. So basically it's a beast. Just unless the US government say, well, we're going to overhaul everything from infrastructure to regulations. I don't think that will happen anytime soon. Thank you, everyone.
Thanks for joining us, and then this is the end of today's webinar. And thank you.